All right, so hopefully you all, at least those of you who are coming to class, did a class evaluation. If you didn't manage to finish, you can just do it in some other time. As I said, this is your time to have your voice heard, both by the professor and by the administrators at the university. So do take advantage of that. As I said, I personally always read all of these recommendations and try to implement them in the future installments of the class. Okay, so let's start with the lecture, but before, as usual, let me remind you of a few admin things. Yakit, I'll get to you in a moment. Um, First of all of these things that I'm going to show you are on the Brightspace under announcements. So do make sure to read. So when you go to Brightspace and click on announcements, all the past announcements are there. One of them is from October, explaining to you how to do ask things about your grades and how to dispute your grade, and ask explanation of what the points are docked for. So the main thing is you first have to go to the office hours of TAs, to the live office hours, and they're going to explain what they removed the points for. If they made a mistake, they're going to correct the mistake. If it was in the grading scheme, then they're not going to correct it because everybody was graded the same. It would imply regrading 500 students. If you still, after talking to the TA and clarifying with them, if you still have some dispute, then only you come to me, to either my office hours, or try to email me to figure it out. Okay, so that's about that. The procedure for that was already a month and a half ago explained. Another thing is please pay attention that I provided extra test cases for assignment 6. That's also in the announcement, and this was about bonus, what's the procedure for the bonus. I think, and don't forget that next Wednesday, so what we're going to do today, we're going to start with recursion. We are left with 3 more lectures, so we're going to do recursion in all 3 of these lectures. So this month, today, Wednesday and Monday, we're going to do recursion, and then on Wednesday, you have your last test, and then we're done with the class. So your last class, don't forget, will be in class, but as university inform you on Wednesday, you're going to, so next Wednesday, we are following Monday's schedule. So to figure out when is your test, you look at your Monday schedule, but the test is on Wednesday, but according to Monday's schedule. Okay. So let's start with the lecture today. So we're going to do recursion, as I said in the last 3 lectures. So let's start. What I want first to do is I want to look at a problem. I'm not going to necessarily start with the problem solving. I'm going to start with trying to show you the mechanics of recursion, how it works. Somehow, I think first you should see how it works, and hopefully once you understand it, then when you're trying to solve the problem using recursion, at least you know how recursion works. So let's see what I mean by that. So the first example that I'm going to do, I'm going to write a function. I call it silly printer. And what I want this function to do is if you give me a positive integer n, I want, Jason, can you put your head down, please? I want you to, given a positive integer n, I want this function, my solution, I want it just to print numbers from n all the way down to minus infinity. Okay, so first, if you gave me n, I want to do print n. Okay, so that's going to print n, but then I wanted to print n minus 1, n minus 2, n minus 3, and never stop. Okay, so I already coded this line of code, print n. I can just then say, okay, I'm happy with this code. I can just call this function, silly printer, again, so it can execute this code, but I'm going to call it with a different argument, with different value. What is it that I want to print next? Silly printer n minus 1, right? So after n, I want to print n minus 1. So after n-1 is printed, well, this one is gonna, let's see what's gonna do. Okay, so let's see what this does. Right now it doesn't do anything because I didn't call it in the main, but let's say I call this function in the main. I call do silly printer 4, for example. I'm calling it with n is 4. Okay, so I do that. Let's say I mark this so we see what's going on. Okay. All right, so this is what it does. So those of you who haven't seen recursion, this may look like complete magic. So let's try to understand how this happens. Okay. Another thing I want you to see, so it seems that if I gave you a problem that says write a function that given a number n, it prints numbers from n all the way down, all the integers from n all the way down to minus infinity. So this looks like, you know, this is one type of solution and it looks to be correct. In fact, it is correct. And let me kill this terminal. I'll show you what is. Okay, so because idle, as I showed you before, idle is kind of slow and idle's kind of slow in printing. So let me show you what happens when you run this program in a terminal, because terminal is kind of, it's much faster. So what we want to do, Python, this program is called blah.py. I run it, poof, and something happened. It should be printing to minus infinity, right? So it should not be stopping. And it looks like it was really doing it, printing from, where was that? Printing from 4 all the way down happily to minus infinity, printing, but poof, about 991, we have a crash. Okay, so let's try to achieve two things now. Both understand why this prints what it prints, but also understand at the same time, because actually the same thing explains why we had a crash. Although mathematically, this solution to the problem I told you, print the integers from n all the way down to minus infinity, this solution is correct. Mathematically, it's correct. Okay, so for that, first let's recall what we did to understand why it crashed and how this works. Let's briefly recall what we did in the last class when I said I want you first to understand this. So let's look, I'm not going to analyze this again, we already analyzed it, but what I want is to point out this. The program is running. Okay, I want you to pay attention what's going on at this moment in time, in program execution. This program is still running. Actually, you can see this is step 12 of 20 of this program. Okay, so at that moment in time, let's see what do we have here on the right-hand side, which is showing us what's going on in the memory with our program. What type of memory resources our program is using. As I already explained, let's look at this picture. There are two sides. There is, when you're looking at this, I hope it's the same. This is not reverted. On the left-hand side, it says frames. This part of memory, so basically your program gets, think of it as two parts of memory. The left side here that says frames, it's called a stack. It's a well-organized memory, and I'll explain what that means. And on the right-hand side where it says object, you get what is called a heap. And there you have unlimited space. It really, nothing can go wrong there. So your program gets a stack, organized parts of memory, and a whole pile where it throws your objects that you're creating, and you have no limitations. Whenever you call a function, that function, you can think of it, you see that there's data about this function, and Python keeping tracks which functions are running and who called who, and that type of data is on the stack. Okay, so if you look at the stack, you can ask yourself how many functions currently are running. So we have here 3 functions posed. Let's call main a function as well. So main is posed, f is posed, g is posed, and h is running. So we have 4 functions currently running on the stack. 3 are posed, but they are running, they are there, right? Okay, so at this moment, you have 4 functions running on the stack. This is what I want you to keep in mind, and you're going to see the same behavior with recursive call. And then, you know, when this function h terminates, then when it returns, that function returns the control to the caller. Now we have 3. But what you're interested in, so this was in step 17 of your program. So what you're interested in across the whole run of the program, what is the maximum number of function at any one time that you have on the stack? Okay, so for this program, if we run it all, finally in terminates, you will say the maximum I ever seen on the stack was 4 functions. Okay, so let's see what happens with recursive calls. All right, so let's run this. So we're going to run on the, by run, I mean, we're going to run it ourselves by hand. And this is something you need to learn how to do, both to understand recursion and also to be able to answer questions of the type, what's the height of recursion and things like that. Okay, so this is not something typically that you can just eyeball. Okay, so it helps with understanding. So basically what we are, and it also helps with, if you have a question of the type which you're going to see in your labs and things, like what does this print? Of course, without typing, you need to understand why something does. Then you need to be able to do this type of tracing of recursive function call. So let's see, to understand, for those especially for whom this is new and those who is not, because for most of you height of recursion is new. That's what we're going to understand now and why that code crashed. Let's understand how this runs. So let's do it exactly on this example. So what is it that, let me, there you go. So, all right. So what is it that is going on here? So let's trace the program. So a main starts running and it has, so first we have a main starts running, and first thing that happens, it calls a function SL. I'm going to just put SL for Sally printer with a value or argument 4. So that means that actually in that moment, main automatically pauses. So this, I'm drawing the same thing that you saw in Visualizer. Okay, so you have a frames, or this is the stack that I'm drawing what's going on in the stack. Currently only main is running. Okay, but now it pauses. And what starts running is a silly, I guess I should say SP, silly printer. So what starts running here, sorry, I didn't wrote this correctly. Okay, so main pauses and silly printer function starts running. In fact, it is silly printer with argument 4. So this function here starts running and it gets assigned, 4 gets assigned to local variable or parameter 4, to local variable n. So silly printer with n is 4 starts running. So its function says print 4. Okay, we print 4. Function prints 4, and then comes to this line. So, and there we see a function call. So we have a function call of silly printer n minus 1 is sent. What n? Well, n of the function running. That n is 4. So this function, silly printer n, calls silly printer with value 3 and pauses. Okay, so the new function starts running. As every other function, it starts at the beginning. Value 3 is assigned to a local variable of that function. So now this function that currently starts running as n is equal to 3. We come here, it says print n. Which n? Well, n of the function running. The n of the function running is 3, so that gets printed. That function that is running moves to the next line. It says silly printer, it sees a function call, it says call silly printer with value n minus 1. What n minus 1? Which n? Well, n of the function running. So that's 3 minus 1, that's a 2. So here, this function calls a function silly printer 2. So that one starts running and this one pauses. Okay, so silly printer with argument 2 starts running. So therefore, as always, it starts at the beginning. It has its own local variable or parameter n. It gets assigned value 2. What does that function start running? It prints 2. Right after that, it has a call to a function, silly printer. What value does it send? N minus 1, which n? Well, n of the function running, that's a 2. So silly printer 1 starts running, and silly printer with value 2 pauses. So this one runs now. 1 is sent to a local variable or parameter of that function. So silly printer when n is 1 starts running. It starts executing the body of the function. What does it say? Print n, which n? N of the function running. So it prints 1. Next thing it sees is a function call to a silly printer function. What value does it send? N minus 1. Which n? N of the function running. So it's 1 minus 1, that's a 0. So this function that was just running pauses, and the function with silly printer 0 starts running. So as every function starts at the beginning, assigns 0 to parameter n, so local variable n, that function starts running, print 0, okay, and so on. All right, okay. So let me, at this point, so hopefully you see at least some of the reason why things were printed, 4, 3, 2, 1, and so on. All right. So let me go back to that code and say, okay, I don't want to crash this code. And actually what I want is to write a type of program that we wrote at the very beginning of the semester whenever we got to the loops. The first thing we wrote, we said, okay, let's write a program that does a countdown from some positive integer n all the way down to 1, and then we print blast off, like we want to send a rocket to space. So what we want here, I want to modify this code such that when it gets to 0, it prints blast off, and otherwise it just continues doing what it was doing. So we have if n is less than or equal to 0. So if we get down to 0 from a false, here we have a precondition that n is a positive integer. You can assume that for what we're doing. So what did I say? We do print blast off. Okay, otherwise I do the same thing. I do what I was doing. Okay, so the only thing I changed here is that I added that condition that if n is 0, that you print a blast off. So let's go back to what we were tracing. So let's see, first of all, what this does. All right, 4, 3, 2, 1 blast off. So let's go back to this trace. We were here. Okay, so we were here. This function, so this function s with n, s silly printer with n is 0 starts running. We are here on the bottom. It's not paused. I don't know why I wrote here that it's paused. This one is the one running. N is 0. We come to this condition and we test, is it less than or equal to 0? The answer is true. So the function prints blast off. Okay, so now hopefully understand why it did what it did. And let's see now what's going on. This function, now you leave so this function with n is 0 was running. You leave this statement, there's nothing else to do. So that function, any function, when it's done, it terminates. So it's off, once it terminates, it's off of the stack, right? So let's notice at this particular moment in time, this function here, silly printer 0, is about to terminate. Okay, so that's going to be next step. But before we do that, let's pay attention how many functions, how many silly printer functions do we have on the stack, or rather, equivalently, how many silly printer functions do we have currently running? Anybody?
5.
5. You just count, right? 1, 2, 3, 4, 5. Okay, so we are tracing our own code, and so far the maximum is 5. Let's see if it stays that way. So let me remove these things. So this silly printer 0 function has nothing else to do, so therefore it terminates. Let me just indicate it like this, so it's not on the stack anymore. And it returns the control to the caller Who called silly printer 0? You can just look in the drawing, look up the function right above. So silly printer with n is 1. What do we have up? So silly printer with n is 1, call silly printer with n is 0. So this one resumed. So that one, now this one can continue running. It was waiting over there. So silly printer n with n is 1 printed 1, and it was waiting over here for silly printer 0. This one just returned, and then silly printer 1 realized, oh, I have nothing to do, so I should terminate and return the control to the caller. So silly printer n is 1 terminates and returns the control.
Oh, oh, sorry. I was about to say I couldn't see what you read.
So it returns the control to the caller. The caller of silly printer n is equal 1 was the one above, so it's the silly printer with the n is 2. So this function now resumes. The same thing happened after printing 2. That function was waiting over here for silly printer 1, which just returned now. But then silly printer 2 realized there's nothing else to do, so I should just terminate and return the control to the caller. And the caller is this one returns to the silly printer with n is 2 was called by silly printer with n is 2 with n is 3. So that one returns. Hopefully now you see the pattern. So that one now can resume. It just printed 3. This one now, it was waiting over there, but silly printer 2 returned. It realized there's nothing to do, so it terminates and returns the control to the caller, which was silly printer with n is 4. That one was waiting over here after printing 4, and now it's realized after the silly printer 3 returned, there's nothing to do, so it terminates and returns the control to the caller, okay, which was the main. And in the main, there's nothing else to do, so that's it, okay? So we saw that, first of all, we saw why 4321 Blaster was printed. So hopefully now at least you understand mechanically what happened. How did this print? How did a function like that print what it did? Why is it called a recursion? Because inside of a function, you are calling a function with the same name, okay? Often you hear this expression, the function calls itself. The function doesn't call itself. What is a function called? That just means execute this. So when you come to a line like this, you are just saying execute the code that is inside silly printer function. Okay, with what value? Well, this time with this value. It's just a separate program, but it's just doing the same code. Okay. All right. So let's go back here. So hopefully now you understand. So what were the two goals? Were to understand why it prints, so mechanics of recursive calls. And second one, to understand why did it crash when we let it run to after printing about 1,000 numbers. Okay. So as we have seen in this particular example, when n is 4, the maximum number of functions we had at this, on the stack running at the same time was 5. But and this thing that I'm calling maximum number of functions running on the stack at the same time, it has a different name. It's called height of recursion. So this is a recursive function because you see a call to the same function name. And the height of recursion is in the run of that function, what is the maximum number of these functions that you can ever see on a stack during the run of that function, okay? So we have seen that we run it, when we run it with n is 5, the height of recursion is with n is 4, the height of recursion is 5. What about for general n? What is the height of recursion of this function? Or rather, what is the maximum number of functions running at any one time on the stack for general n? What about when n is 100? How many functions we're going to have on the stack maximum?
101.
101. And more generally for n?
N plus 1.
N plus 1, exactly. N plus 1, exactly. So this recursive solution to a problem of printing doing a countdown. Let's stick to this one. Doing a countdown from n down to 1, it's a correct solution with a height of recursion n plus 1. Okay, so at some point, if you want to do countdown from 1050 down to 1, you're going to have 1051 functions on the stack. So let's try to do that. Okay. All right, so let me run that in the terminal rather than the main. So if we do it with 20, no problem. As I said, mathematically, the solution is correct. No problem. But actually, just so we don't wait for this slow terminal, let's run it here. So let's say for 500, that works, just too fast, but it works. Let's see this one. Okay, so that one crashes. All right, so it starts in about 1050, and when it gets down to about 50, it crashes. Okay, so maybe already if I put, let's say 1000, yeah, this one already crashes at 1000. Why is this? So when you're doing, remember, height of recursion is telling you how many time you're going to have at some point, how many functions you're going to have at some point running at the same time on the stack. And Python allows about 1000 maximum. So while on the heap, on the right-hand side of the memory, you can have arbitrary amount of memory you like. On the stack, in that ordered memory that keeps track what functions are running and which function call which other functions, you get a limited amount of space. So it's about, in Python, it's about 1000 functions you can have maximally on the stack. And it's the same thing in other programming languages. You get limited amount of space on the stack. The number is not the same. It's in Python, it's about 1000. In Java is considerably more than that, but it's still limited. Okay, so it's easy to blow the stack. That's what happens. So you get here, what's the message? Maximum recursion depth. Some places you're going to say recursion depth, some places you're going to say recursion height. It's the same thing. So you exceeded what Python allows you for the maximum number of functions on the stack. Okay, so that's why it crashed. Why are we talking about this at this point? Because it's only when you get to recursion that you can basically have 1000 functions on the stack. Up until now, the only function, the maximum number of functions you could have on the stack was basically the number of functions you wrote if you didn't use recursion, right? So to have 1000 functions on a stack, you should have like 1000 different functions and call each one of them. One of them is calling another, so call each one of them at the same time. Who's going to do that? So there was no chance you're going to have that. The way you get too many functions on the stack is by having a recursive call. Function keeps on calling its own code, if you like. Okay, and that's one of the reason in assignment number 1, you had to write a PEL function whose definition is naturally recursive, but I gave you on purpose that you have to test it with a big number. I don't know if you remember. So those who use recursion would have to realize that it's not working for all integers, and you're using recursion and you don't necessarily even understand. Some already know this, that there's something to learn there. So and also to make you use material that we already have seen. Okay, so that's what I wanted to show you about the mechanics, if you like, of recursive calls. You can see exactly the same on Python visualizer that is drawing exactly the same thing. Okay, so you can see here, that's what we were doing. So what do you have here? 1, 2, 3, 4, 5 functions on the stack. And why is it n plus 1? It's because when you're calling silly printer function with n, that one calls silly printer with n minus 1. silly printer with n-1 calls the one with n-2, and -2 calls the one with n-3, and so on until you go down to 0. So you end up with n+1 functions because we are going from n to 0. Okay, so this is what what we were drawing by hand. The same thing is here in the visualizer. By the way, if we go back to that solution where we were, let me see if that's what I want to show you next. Yes, if we go back to the solution where I ask you write a program that prints from n to -infinity, although the solution is correct, you see that Python cannot handle that type of solution. But let's see if we use so-called iterative solutions, as solutions using the loop, not using recursion. What would be an iterative solution of that problem? Let's call it a silly printer I for iterative solution. You can do something like while true, print and new n is now n-1. Okay, so a program like this, let's run it here so you can see it. You have seen that this one crashes the program. Silly printer 4 crashes the program, but if I do its iterative solution, this is going to run forever. There's nothing to, in fact, it was running when I was showing you the terminal, it was running from the previous class. So I had to forcefully terminate it. You have seen it's already printed about -3 million. There's nothing to crash this program. This program is never going to stop. Your computer is going to crash before this crashes. So why is it that this one runs forever and the other one crashes? This is a simple question. I mean, there's
only one function on the stack.
Exactly, there's only one function call, and that function has one variable, and it's an integer. And all that is happening, you are doing -1 from that integer. And remember, in Python, you can have arbitrary large integers. And why is that? Actually, because your integer lives on a heap. So it's just making bigger and bigger integer, taking more and more space on a heap. But there you have unlimited space. Okay. So you see here that both solutions are correct. But in a recursive solution, you have this additional thing to keep in mind, which is that you have a limited amount of space on the stack. Okay, let's not count. You see now that we are counting how many functions are on the stack. Let's not confuse counting how many functions are on the stack and counting number of operations, what we were doing up until the class today. These are two different things. For both iterative and recursive solution, you should care about number of operations because that determines the amount of time you're going to wait for your solution. So that's big O, counting the number of operations. But then in addition, in recursion, you also care about height of the recursion. Okay, so I'm going to stop this. Let's now finally kind of solve the problem. And I'm going to start, of course, with the one everybody starts with. It's a classic. So I'm going to do the same. I'm going to start with factorial. So let's start. Let's design a function that computes a factorial of an integer. So let's go back to my notes so I can explain what a factorial is for those who don't know. So first of all, factorial. So here's how you denote it. Factorial of a number is denoted n and then exclamation mark. That's how it's denoted in math. That means n factorial. And it's only defined for numbers n that are non-negative integers. So basically, you cannot ask what's factorial of 3.5 or what's factorial of -20. It's only the main of this function is non-negative integers are the only things for which it's defined. Okay, and how is it defined? It's defined as follows. So it's defined that if n is 0, so 0 factorial, I just tell you what the answer is. The answer is 1 factorial, so 0 factorial is 1. So 0 factorial, you don't have to color this exclamation point, is 1, okay? And for all the other values, so for all the other values, which is all positive integers, factorial is defined as n times factorial of n minus 1. This is n minus 1 factorial, okay? So you have n times factorial of n minus 1. That's the definition. So let's see a few examples of what this gives. Okay, so we already seen for n is 0, 0 factorial is just, you are just told it's 1. What about 1 factorial? For everything else, you just go to the formula. It tells you, you do n is 1 times n minus 1, that's 0 times 0 factorial. Okay, 0 factorial, we already know it's a 1, so that's equal 1 times 1 is equal to 1. So now we know 0 factorial and 1 factorial. Okay, what about 2 factorial? You go to the formula, it says that's a 2 times 2 minus 1 factorial. That's 1 factorial. 1 factorial, but we already know 1 factorial is 1, so we can say that's 2 times 1 is equal to 2. So far, a little bit boring. Let's say 3 factorial. That's, we look at the formula, 3 times 3 minus 1, that's a 2, 2 factorial. We already computed 2 factorial, it's a 2, so that's 3 times 2, that's 6. Okay, let's look at the final thing. Well, it's not final that I'm gonna do by hand. 4 factorial, we plug it into formula, it's 4 times 3 factorial. We just computed 3 factorial, it's 6. So that's equal to 4 times 6, and that's 24. All right, let's code this. Okay, you're gonna see this is so easy. You literally, I mean, in a sense, you just copy this formula. Okay, so what do we wanna do? We wanna do, let me move this so you can look at both at the same time. All right, so I'm gonna write a function called factorial. We wanted to compute the factorial of a number, and we have a precondition that n is an integer, non-negative integer. Okay, I'm not gonna be writing these things. Okay, let's look at this formula. What does it say? When do we immediately know the answer? Okay, if n is equal to 0, I know the answer immediately. Let's say I want my function to actually return the factorial, so I do return 1, because I know the answer already. Okay, otherwise, I do this. Okay, what does it say to do? You should do n times factorial of n minus 1. Okay, so I should call this function factorial of n minus 1. There we go. Well, in addition, I should return it because we said the function should return that value. Okay, so let's see if it's working. I mean, we literally copy-pasted the function. The definition of factorial. All right, so let's look at this example. Did we get it correctly? This is 24. Let's see, factorial of 4 should be 24. Indeed, it's correct. Let's see, factorial of 10. You see how far, this is one of the very fast growing function. It's exponential. So it goes fast by, grows super fast. Okay, 500, ginormous numbers. Okay, so let's understand how this works. Okay, let's do another one of those runs by hand. So I think, I don't want to do 4, it's too many. Let's do this one. We have in the main factorial 3. Okay, so let's say we are looking at a call of a factorial of 3. Let's say we want to print it. All right, so it's a 6. Did we get a 6 here? Oh, that goes there. Yes, it's a 6. 3 factorial 6, so our answer was correct. All right, just for the tracing purposes, I'm going to separate computation and returning just because it's a little bit easier to see what is going on, and then I just return result. Hopefully by now this should be blindly obvious that this is the same code. So let's trace it on this example. So as before, we have a main starts running over here, but immediately we have a call to a function. So main pauses and calls a function factorial 3. That function starts running, so factorial 3 starts running. Value that is passed to it is 3, so this factorial function has local variable 3. It's not equal to 0, so it comes to this line. It needs to compute results. It needs to compute something. What does it need to compute? 3 times something. But that something is a function call. So this function actually calls here a factorial of what? N minus 1, like before, which n running. So that's factorial of 3 minus 1, that's a 2. So this one pauses and this new function starts running. Okay, so this function starts running. As every function starts running at the beginning, first 2 is assigned to n, so this local variable n is 2 exists in this function. It's not 0, so we come to this line here. This line tries to compute 2 times something, but that something is a function call. Which function call? It calls factorial function with the value n minus 1. Which n? N of the function running. So that is 2 minus 1, that's 1. So this function pauses and this one starts running. As every function, it starts at the beginning. 1 is assigned to n, so function currently running has a local variable n is equal to 1. It's not equal to 0, so it goes to this line. That line needs to compute something which is 1 times something, but that something again is a function call. The factorial function, you send it value n minus 1, which n of the function running, that one is 1, so 1 minus 1 is 0. So that function pauses and function factorial of 0 starts running. Okay, so it starts running at the beginning at every other function. 0 is assigned to n, so n, local variable n gets created of the function. We come here, it says, oh, n is equal to 0. Yes, this time, yes, finally something's going to start happening. It says return 1. Okay, so this function is running. Before we start returning, let's again pay attention. At this point, how many functions factorial is currently running? I mean, we can count them.
4.
4. Actually, 5. Oh, 4, you're right. Yes, we started with 3. So 1, 2, 3, 4. Okay, so we start from 3, go all the way down to 0. So 4 of them are running. Okay, let's remember that. Okay, and now let's see what's going on. So this function that is currently running, the one on the bottom of recursion, if you like, it's done. It's going to return, because it knows the answer, it's going to return its answer, which is 1. Whom is going to return it? It's returning it to the caller, which was factorial of 1. Factorial of 1 was waiting over here for that value. So this function returns a 1. This one here was waiting over here for that value. So now finally it can do the computation. So factorial of 0, after returning 1, just like any other function, it terminates. Once you terminate, all the space you got on the stack is gone. That function is not on the stack. It's not running anymore. It terminates. So this is what is on the stack right now, what you see on your picture. I don't know where you see it. Hopefully I'm pointing in the right direction. Okay. So this function factorial 1 can now resume. So that function, so this function resumes running. It was waiting over here for this value 1 in this line here. So now it actually can finish computation. 1 times 1 is 1. So this result thing is 1. It goes to the next line, says return 1. Okay, so this function currently running returns 1 to the caller. The caller was factorial of 2. it was waiting for that value over here. Okay, so it receives that value. This function, after returning 1, it terminates. It's gone from the stack and returns the control to the caller so the caller can resume. It was waiting for this value here, 1. Now it got it, so it can finally do its n times blah, which is 2 times 1. It can do that. That's a 2. So that one can compute 2. What's stored in result is now 2. Okay, so then it goes to this line, continues the program, says return result. What does it return? Returns 2. So this function returns 2 to its caller. Its caller was factorial of 3. So the function, after returning 2, it terminates. This function was waiting for that value, 2, over here. Finally, it got it. So now it can finish the computation. That's 3 times 2. That's a 6. So 6 is stored in result and 6 is returned. Whom does this function return? So this is 6. So this function returned value 6 to the caller. The caller was the main. So main finally receives 6 here and can resume. And when it resumes, it now knows what to print. It prints 6. Okay, so that is how that runs. Hopefully you can see, at least through this mechanics, that this is not some magic. Each one of these functions did a little bit of work. In fact, each one of them did one multiplication. Okay, it was multiplying with something that with n times the result that they received from the other function. Okay, so we have seen that in the case when n is 3, the height of recursion, or the maximum number of function on the stack running when we were doing this, was 4. So when n is 3, height of recursion is 4. What about general n? What's the height of recursion of this factorial function? So function factorial of n calls function factorial of n minus 1. N minus 1 calls n minus 2. N minus 2 calls n minus 3. Each one of these calls is one function until we get to n is equal to 0. Only then we start returning. So what's the maximum number of functions we can have on a stack when we're doing factorial of n?
n plus 1.
N plus 1. Okay. It's coincidence, kind of coincidence. You will see other example where it's not n, it's not always n plus 1. But from this, you should now suspect, okay, that looked good when she was, so it worked for factorial 500, it worked. That means the height of recursion was 501. It worked for 101, for 100 because the height of recursion was 101. So we were not in trouble. But it should tell you that, okay, if I try to compute 1050, the height of recursion should be over 1000. So there you go. So our solution, although mathematically and even algorithmically is correct, it crashes in Python due to memory limitations that we have on the stack. Okay. So let's end with solving a different problem. So what is the next that I want to do? Yeah. So let's do something that, okay, this one factorial, really we copy pasted the definition in effect. That's why you see that it's tempting. If you go back to assignment number 1 or 2, actually, it was assignment number 2 where you had to do PEL function, I think. You would see that the code is actually way easier if you use recursion. You just copy paste the definition of PEL number. That's why it's so tempting to use recursion. You literally don't have to think sometimes. That's how much simpler solutions can be with recursion. Okay. Simpler once you have some feeling about it, right? If it's completely new. But even if you knew, you probably appreciate that we just copied the definition of factorial. You may not necessarily know exactly why it works, but we really just copied the definition. Okay, so in terms of coding, it should at least be clear what we were doing. All right, but let's do something else. What I want is, let's go back to something that we did way back when, and hopefully by all of you is by now easy. how do you sum elements of the list? So let's say I give you a list of numbers and I ask you to sum all the elements of the list. So we know how to do this iteratively with loops, but let's figure out how to do it with recursion. So what do I want? I want a function, I'm going to call it summer, that has a list. And let's say a list is a number, a list of numbers, and I want it to return the sum of these numbers. Okay. So when you're designing recursive solution, ask yourself two things. First thing, when is the answer trivial? When is there basically nothing to do? So when we did recursion, when we did factorial, it was in the case n was 0. We know the answer from the derivation, we just return 1. Okay, so let's go back to this problem. Two questions. First one, let's address first. When is the answer, when do you immediately know the answer?
When the len of L is equal to 0.
Yeah, so when len of L, so you can say if len of L is equal to 0, let's say return 0, there's nothing to add up, okay? What's another situation when there's basically nothing to do?
When len of L is equal to 1.
When len of L is equal to 1, okay, we already know the answer. What's the answer?
L of 0.
Exactly, it has only one element, so there's nothing to add. We return that element, that's the sum. Okay, for everything else, okay, we get to the question number 2 that you should ask yourself when you're designing solution. So question number 1 is what are the trivial cases? These are actually called base cases, and often you don't need 2 like this. 1 is enough to stop the recursion, stop from going infinitely to minus infinity. But let me show you what is the second question that you should ask yourself when designing a recursive solution, and is the following. Can I express, this is the question, can I express the solution to a bigger problem, the one that I'm trying to solve, as a solution to a smaller problem? Okay, what does she mean? Let me show you an example. What did we do in a factorial? We are saying solution to factorial of n. I'm expressing it as solution, doing something simple. If somebody told me what is a factorial of n minus 1, it was smaller problems, the same problem but smaller. So I'm expressing here solution to n factorial, I'm expressing it as solution as something simple. I'm doing multiplying n with a solution to a smaller problem. Okay. So, all right, you can say, all right, still that's confusing. Maybe it is, but let's look at what does that mean in this context, what we're trying to do. Let's say I ask you, let me explain what I mean by this. Can I express the solution to a bigger problem as something involving a smaller problem? The same problem, but smaller, right? Okay, so let's say I ask you all right, here's a list of 10,000 numbers. And so on. And I ask you, let's say I wrote it down ahead of time and I ask you, what does this sum to? I mean, nobody would be able to answer. Either you're going to say, I don't know if it's 10,000 numbers, or it would take you God knows how long to answer and probably wouldn't answer correctly. But that's not, the answer would kind of be, I don't know. Okay, what if I tell you this? I tell you that if I take all but first element, in this list, so all but first element add up to 1,000, would you now know the answer to my question, what do these 10,000 numbers add up to?
1007.
1007, exactly. So if you give me a solution to a smaller problem, I can tell you a solution to the whole problem, okay? So here is one way to do it. So I'm saying, how are we expressing? Here's what I mean, expressing a solution to a bigger problem as something involving a smaller problem. In this case, I said, okay, I'm giving you a solution. If I give you a solution, if I give you a sum to all by first element, can you tell me a sum of all elements? Okay, so that's like saying sum of this list L, I'm not writing this, I'm just writing this for human, is the same as saying is the first element plus the sum of the remaining elements. However you. Okay, so we express the solution to the whole problem as something involving a solution to a smaller problem. Okay, so it's the sum of the first element plus sum of the remaining elements. Okay, let's write that down. Okay, so we say that this should be else if. And finally, else if we have two elements or more, return what? L of 0 plus sum of the remaining elements. So all the elements excluding the first element. Well, we have a function for that. And luckily in Python, it's very easy to create a list that doesn't contain the first element. We just slice it. We say start with the first element, index 1, so mean skip L of 0 and go to the end. That's it. So we just, once you have expressed your solution in terms of a smaller solution, you just copy it into the recursive thing. Okay, so let's see what this is. It says, if you have at least one element, at least two elements, return a sum of the first element plus the sum of the remaining elements. Let's see if it's working. Let's first eyeball it. I mean, let's first look at it on understand it on a smaller example, so we at least make sure that the solution works and it's correct. Let's say 1, 2, 0, minus 10. So this should be minus 7. Indeed, we get minus 7. Hopefully you remember. So let's create a little bit bigger list. You know that this produces a sequence of 0 to 99 inclusively, and then we can convert that into a list. So here's a list with 100 numbers. All right. And we want to know, here are those numbers. We want to know what they sum up to. So I send it to this function L, and we get the result. Is it correct? Hopefully some of you know this, that sum of the numbers from 1 to n is what? N plus 1, so in our case 99 plus 1, that's 100, times n, in our case that's 9. This is on the side, divide by 2, and hopefully you know why, but it turns out that's correct. So our thing is working. Let's try it on a little bit bigger list. What about 500? All right. So we have a list with 500 numbers. It seems to be working fine. What is the height of the recursion of this solution on a list with n elements? What do you think? Let's look at what's going on when we're making these function calls. We are starting with a list of n elements. And over here, we are making a call, and the list has how many elements? N minus 1. Yes, William.
Could we have not used the sum function, and then we would use less operations? Because you're being given a list, and it has the sum operation. So we'll just add all the elements in it.
You mean to call the Python sum function?
Yeah.
Of course we can do that. But I mean, we are learning about recursion, and I'm showing you.
Oh yeah.
Okay. All right. Yes, of course you could do that, but we wouldn't learn much through the process.
Oh, okay. I understand now. Thank you.
No problem. So, so the function, first function call, the list has length n, Then that one calls a summer function, and list has length n-1. And then that one, the list of size n-1, that function is going to call this as well. And then that list will have a length n-2 and so on. So we are starting with list. The first function has list of size n, the next function has list of size n-1, the next function has list of size n-2, n-3, all the way down to 1. So what is the height of recursion?
n-2.
I'm not sure why you say that. It's n because we have n calls n-1, n-1 calls n-2. Let's say for 4. List of size 4 calls list of size 3, calls list of size 2, calls list of size 1. So we have, when n is 4, we have 4 functions running. And now n is 1, it's going to start returning. 1 returns to 2, 2 returns to 3, 3 returns to 4, we are done. But it's, again, just like big O notation, we really care about roughly. So this is roughly n. So this solution, again, is going to crash when our list has about 1,000 elements. So let's see that. Let me create a list that has, I don't know, 1,050 elements, just so we make sure that we're outside of a safe range. And then when we call a summer function, it crashes and it tells you maximum recursion depth exceeded, right? So you know that you had too many functions on the stack, okay? More than 1,000. All right, but so far you were thinking, man, it always looks like n. Can something be done about this height of recursion? All right, let's see. Let me ask you something. So it seems all the work is done here. All right, because here, it has 1 element, it has 0 elements. So kind of this is where the work is done. So what does this thing do? It says, if I were to divide work between 2 students, okay, so we need to sum up the elements of a list. Let's say we go back to the starting 10,000 number. And the first student gets 1 number, L of 0. That's what they have to sum up. And the next student needs to sum up all the remaining elements, so 9,999 numbers. So the first student gets 1 number, just writes it down, and the other one gets more than 9,000 numbers to add. Does this seem like a fair division to work to you? Or more importantly, what would be more fair?
If you split up the work.
If I split up the work in equal, right? If I gave you work like this, there would be an outrage, right? So the only fair thing would be to divide the work. The first student sums the first half of the elements of the list, and the next student sums the remaining half elements of the list. So they do roughly the same amount of work. Okay, so let's do that and see if that makes any difference, and why does it make a difference if it does. Okay, so what did it say? Instead of saying express the solution. So what do we express the solution as a solution to smaller problems? Our first way we expressed it was add the first element plus the sum of the remaining element. Our next solution is expressed as sum of the list L is sum of the first half of the list plus sum of the second half of the list. All right, whatever I said with the words. Again, you just write that. And again, in Python, it's particularly easy. We can use slicing. So let's see what we do with the slicing. In the first case, we want first half of the list. We know how to do it. We go from 0, so you skip it. 0 is assumed. To len of L divided by 2. So that's the first list. And what do we do here? This is the first half of the list, this slice. And here we want second half of the list. So I start in the middle and go to the end. So if I'm going to the end, you remember you just omit that number. That's it. Okay, so let's see if that's working. Maybe we can first start with easy example to see if this small thing works. All right, that works. And let's see if this one crashes, the one that crashed the previous version. Okay, it doesn't crash now. Let's try something a little bit bigger. Let's try the example that we were talking about, 10,000 numbers, 1, 2, 3. L has 10,000 numbers. I run it, no problem, it's working. What about million? 1, 2, 1, 2, 3, 1, 2, 3. Do you think this is gonna work? You have to wait a second until it doesn't. So what did we learn? What do we know from these runs? What do we know about height of recursion? What is it that we know for sure? Let's say when we were running this on the list of size million, when we were running this on a list with million elements, it didn't crash. Therefore, the maximum number of these functions running on a stack is what? What do we learn just by the mere fact that it didn't crash?
It's 100 times more efficient than the last one.
You know, it depends really what you mean by efficiency.
You have 100 times more place in the stack, I guess, because at 1,000 it crashed, but it doesn't crash at a million.
So, right. So all we know is that at no point did we have 1,000 functions on the stack. Okay, so this one, even when list has million elements, the maximum number of functions on the stack when we were running this solution was somehow less than 1,000. Okay, we can even try 10 million. All right, so to understand this, again, we need to know why, what's the height of recursion? So let's see this one. I'm probably going to wait a couple of seconds. But it doesn't seem to be crashing. Maybe slow, but it shouldn't crash. In either case, okay, let it compute it, but it's not going to crash. I can tell you it's not going to crash. All right, so there's a row is done. We waited about 10 seconds. So just looking at this, we are at the end of the class. I'm not going to be explaining this. I may do it next time. So in the previous solution, when we did first plus the rest, the height of recursion was n. What is the height of recursion of this function? Anyone? Some guesses? You can guess.
2 to the power of 1,000-ish.
Oh, 2 to the power of 1,000 is a huge number. I'm talking about n. 2 to the power of 1,000 is a huge number, way more than 1,000. So I'm talking
n over
about
2.
Just a moment. I'll get to it. Sorry. Let me just explain. I'm talking about what is the height of recursion of this function of lists with n elements. Okay, so now you can say, because I didn't. In
Is
terms
it
of n. Sorry?
n over 2?
It's much less than n over 2.
Log
You see it
Log
worked.
2n?
You see it worked on lists with million elements. Million over 2 is 500,000. So if we had 500,000 functions on the stack, it would have crashed a long time ago. But somebody just said the correct answer. It's log base 2 of n. This is exponentially less number of functions than the previous solution. Okay. Why log base 2 of n? What is halving? Remember, how do we get a log? You start with something of size n. In the kind of next step, it's n over 2. Then it's n over 4. Each step you divide in by 2. What is going down by 2 in each step? Every time we call, so here we're starting with a list of length n. It calls a sum of functions on a first half now only. And that length of that list is n over 2. And then when this one, with the length of the list n over 2, comes to this line, it calls only on the first half of that. So half of n over 2 is n over 4. And then n over 4 calls it on n over 8. So we will have much more calls, but there will never be more than log base 2 of n functions on the stack. And remember, even for billion, that's 30. So if our list has billion elements, there won't be more than 30 functions running at the same time on the stack. So we are nowhere close to 1,000, like in a previous solution. Only with 1,000 elements, in the list, we were already in trouble. Okay, so I'm going to stop at this point.